Here it is given which one of the following statements are correct. The first statement, the zero-point energy of the linear harmonic oscillator arises as a consequence of uncertainty principle. The second statement, the eigenvalues of a Hermitian operator are complex or real. The third statement, the kth vector is used to represent a wave function. So this thing we are going to analyze these three statements in the quantitative manner. The question, the first statement they are given, the zero-point energy of the linear harmonic oscillator uh, arises as a consequence of uncertainty principle. So the zero-point energy, you got to write zero-point energy is a consequence of uncertainty principle. This is a thing we are going to check whether it is true or not as an uncertainty principle. Actually, in general, this is a true statement, but how it is true, we can ask one question. So once if you are writing the Hamiltonian for the energy, or the in general the Hamiltonian or energy for the quantum harmonic oscillator, that would be equal to delta p square divided by 2m. That means the momentum can be replaced by uncertainty momentum. Same way of kx square or m omega square x square, that x also it has to be replaced by the delta x. So from the uncertainty principle, we know the delta x, delta p we can't measure simultaneously. That has to be equal to or greater than or equal to h cut by 2. This is a uncertainty principle, it says. So once if you are replacing the delta p as h cut by 2 delta x from the uncertainty principle, then you have the energy of the harmonic oscillator equal to h cut square divided by 2m for delta p square h cut square 2 delta x square. So it has to be 4 delta x square. So plus 1 by 2 m omega square delta x square. In general, one must be equal to h cut square 8m delta x square plus of m omega square delta x square. If this energy will be the minimum, that means what we need to find, what is the minimum position uncertainty energy allowed to for the ground state harmonic oscillator. That means if you are differentiating this energy with the delta x, it has to goes to 0 for the minimum energy. So once if you are differentiating this one, you can't differentiate h cut square by 8m, it's a constant. If you are differentiating this one, it has to be delta, just to push the delta x square numerator, it is be delta x square minus 2. If you are differentiating, it is minus 2 delta x minus 3 plus 1 by 2 m omega square delta. If you are differentiating delta x square, it will give 2 delta x is equal to 0. So that is a differentiation of the total energy. If you are differentiating this, if E is minimum, then that minimum energy is constant. If you are differentiating with respect to delta x, that goes to 0. So that minimum energy goes to 0. From this relation, we can find what is the value of delta x for the minimum. So you can cancel these two. 1 2 are 2, 4 2 are 8. So it will give h cut square by 4m. Push it down, delta x cube equal to, here it has to be minus, so it will plus 2 to here, it will get cancelled, m omega square delta x equal to 0. So if I rearranging this one, you will get delta x power 4, that has to be equal to h cut square by 4m divided by m omega square. So you can find what is our delta x. Here if it will be equal to h cut square 4 m square omega square. This is a delta x power 4. Suppose if you are finding the delta x, what it is, the delta x equal to h cut square divided by 4 m square omega square whole power 1 by 4, or else it has to be 1 by 2, because you can write uh, or else this will give the delta x equal to if you are square it everything, then square 1 by 4, it will give 1 by square root 2, so h cut divided by 2 em omega whole power 1 by 2, you can write as it is. This is the delta x. Now you can substitute it here to find the minimum energy here actually in this equation. So once if you are substituting, it will give the minimum energy, the E naught, that would be equal to I am not going to do, just you can substitute here. If you are substituting delta x, the minimum energy it will give E naught, maybe I can write it here. So after substitution here, it will give the minimum energy, that E naught equal to h cut omega by 2. So then the first statement is true. This is the ground state, the ground state energy of the quantum harmonic oscillator. Hence we can shown to be the minimum energy of the ground state harmonic oscillator, quantum harmonic oscillator, is allowed by the uncertainty principle. So the first statement A is true. The second statement they are given, eigenvalues of Hermitian operator, eigenvalues of Hermitian operator is or complex or real. Actually this statement even it says the eigenvalues of Hermitian operators is either real or complex. So this is not true statement. If it is Hermitian operator, then that eigenvalue has to be real. That is the thing we proved in one of the problems. So you can directly put this statement is wrong statement. Then the last one, it is given the Kate vector is used to represent a wave function. Yes, that is true. So if you are using the Kate function, usually the in the bracket notation, this is a bra, this is a Kate. So in general, so for Kate notation means this is a bra, this is a Kate. That's why it is saying bracket notation. So this Kate notation in general, it is representation for the wave function. So that is a true statement. So from the above discussion, we got the 0-point energy of the linear harmonic oscillator arises as a consequence of uncertainty principle. That is the right answer. The eigenvalues of Hermitian or operator are always real, not a complex. So this is a wrong one. The Kate vector is used to represent a wave function. That is a right. So the first and the third options are right. Then the second one is wrong. So the right answer is C.